It's a real pleasure to be here. Thank you for giving me this opportunity to talk to you today. Indeed, I'm going to talk about computing and planning with large generative models. So I'm going to break the talk and the discussion into three distinct parts, and they'll be rather different from each other. And I have to confess, I'm not going to start out by talking about planning. I'm first going to actually focus on considering large language models simply as a form of computational device, and maybe present a little bit of theory and a little bit of grounding in what that might mean, just to make sure that when we start talking about other applications and planning problems and so on, that we're sort of clear about some of the fundamental assumptions and some of the fundamental understanding. After I've established this kind of foundation, I'm going to pivot fairly distinctly to just presenting a couple of small studies that we've been conducting in the last year or so around planning problems, trying to see how we can leverage large language models as a tool to help kind of broaden the scope of planning problems that we can contemplate and take on, and hopefully, ideally, at some point, maybe even improve the performance of planning engines. And then finally, I'm going to, for the third part, I'm going to share some recent work that I find quite exciting, but it's maybe a little bit ambitious, is actually to use video diffusion models, like generative models of video, as a foundation for sort of expressing and solving real-world planning tasks, in particular sequential decision-making. Now, I am indeed an outsider to this community, so it is my intent to try to build a bridge. But up front, I have to tell you, just like you, I'm trying to make sense out of this whole large model thing. I think it's crazy. I'm going to, bring up a bunch of questions. I'm by no means going to be able to answer all of the questions that I raise around this space. But I'm going to attempt to identify what I think are a couple of key gaps that still remain. And also maybe try to share at least my current best attempt at thinking things through and trying to have an organized perspective on how large language models, large generative models kind of relate to our more classical thinking about formal computational devices and how we might sort of strive toward getting a kind of a more generalized and ambitious and unified approach to this whole scope of computation. Anyway, we'll see. So I'm going to start now with part one by just sort of stepping back and trying to think about large language models as compute engines. Now, forgive me, I think even before I get to that, I probably need to tell the story of how we got to where we are. So just, just as a warm-up, some background, the prehistory about large language models. So I'm sure you probably know that language modeling is a sub-area of natural language processing. It has been a sub-area for decades in NLP, but for most of that history, it was like, it was an academic sub-area. It wasn't really considered to be a high-impact, prominent area of natural language processing. But I was always attracted to this because I always liked the idea that language modeling was very objective. There wasn't like some sort of human subjective assessment of the quality of the output. The goal is you literally build a conditional model of discrete token generation. So if, the equation up there is a language model abstractly is quite simply just a map from a string, which is a finite length sequence of symbols from a finite alphabet, to a conditional distribution over the next discrete token. This is objective if you want to maximize likelihood over a training corpus. There's just an objective log likelihood. There is no subjective assessments involved. Again, this was largely academic until recently, so let me sort of build the bridge from there to here. Now, just two other preliminary things I want to say is that even though a language model itself, simplistically is a conditional distribution over the next single token, you can, of course, imagine this so-called autoregressive kind of extension where you can now produce conditional distributions over entire output sequences, or more generally, it's really a map from an input string to a conditional distribution over a tree of possible outputs. Okay? Now, when I try to relate language models to computational devices, I'm mostly going to be talking about the deterministic regime. So I'm going to assume, generally, unless I say otherwise, that I'm going to use greedy decoding or zero-temperature decoding, in which case the language model is essentially a string-to-string map. There's some input string in and some output string or sequence that gets produced. Okay, and so we've seen this journey evolve, over the last decade or so. And so on the sort of the architecture side, we've seen these models go from n-grams to recurrent neural networks to LSTMs, and more recently to transformers. But I think it's not really just the progression in architectures that have led to these sort of dramatic advances. It has, of course, been this simultaneous expansion in the amount of data that we've been sort of training these models on, the size, the parameter counts and the size of these models. And the amount of compute, obviously, that's been thrown at these. Now, this is a little bit poetic. This is not the case, but you could literally imagine trying to ingest the entire corpus of every human-generated string in history, which, okay, that sounds crazy, but it is a finite set. It's a large set. And as a proxy, you can imagine all sort of, electronically captured human-generated strings on the internet. And, nowadays, these models are indeed trained on some non-trivial fraction of that. And if we think about this, there's going to be several things that are not surprising. So it isn't too surprising to see as the models, the architectures improve, the amount of data increases, that these models, sort of start to respond to input strings, with increasing fluency. Previously we'd be impressed if they generated actual words or something that looked like an actual phrase up to maybe an actual sentence. But we've pushed down to a point where now these models respond fluently with entire paragraphs, pages, documents. It's quite impressive. And we also really shouldn't be too surprised that just simply by virtue of capturing these conditional, distributions, that there's a sense in which these models seem to know an awful lot, right? So if we ask a basic question, it seems to respond with answers that, demonstrate apparent knowledge of entities and relationships and so on in all of this human-provided text. This was not surprising, but starting about 5 years ago, there was a very persistent a chain of I would say a chain of rather dramatic surprises that I think caught us all off guard, and none of it was anticipated, and none of it was designed in the architectures or sort of the data collections. It was just this kind of side effect that we didn't see coming. So let me just walk you through a couple of those. So the first surprise, in my view, was the GPT-2 paper. I guess this is about 5 years ago now, was this phenomenon of in-context learning. And here, quite simply, is this idea that, for example, by the way, these models are trained not on all languages. So French, English, Chinese, it's all in there. We would see this behavior that if I prompt or I provide input strings in some language like French, the models generally respond in French, as long as there isn't some bug with the tokenizer, and sometimes you get Chinese and so on. But generally speaking, French input, French output, English input, English output, and so on. And here there was this really clever and surprising demonstration that you could get translation as a byproduct by simply taking the model that was already pre-trained and frozen and providing it with like pairs. Like if I give it now a French sentence followed by an English sentence, that's a translation, and another example of a French-English translation pair, and so on and so forth. And then you provide a French sentence as input. Kind of remarkably, the model would respond in English, and it would respond in English with some, admittedly here it's a poor, attempt at a translation. And so this, I think initially in the natural language processing community, led to a bit of a revolution in thinking, which is up to that point in time, NLP, like the rest of AI, was sort of fractioned into sub-areas. Like translation was a sub-area that was distinct, profoundly distinct from other sub-areas and other sub-problems in natural language processing. And we started to see like these kind of generalist models that were able to support like the whole range of natural language processing tasks. And yet the model was never trained to do this. It was only trained to do next token prediction over the corpus. And perhaps in the corpus there's like the Canadian parliamentary proceedings with French-English translations and so on. But nevertheless, it was just some free phenomenon. The surprises, sort of continued from there, right? It was subsequently discovered that apparently, these models can do some form of instruction following, where instead of like giving examples or, exemplars of the kind of, task or behavior you're seeking, you could just literally give it commands like you are a helpful assistant, or I'm going to ask you some nonsense questions and I want you to explain why they're nonsense or something. This was not designed, it was not engineered into the systems, and yet we saw these kind of remarkable, behaviors of these models that they were able to respond coherently and fluently and apparently with some understanding of the instructions. Now, of course, you can cherry pick positive examples, there are all kinds of negative examples. But there's something going on here that is not ignorable. Okay, last step in the story here is some work I was directly involved in. And this for me was the turning point, is this phenomenon that has since been called chain of thought prompting. And so the scenario at this point in time is, this was actually back at Google Brain, is that there was, some big studies, large models, and we were looking at these math word problems, which, you get these little puzzle problems like you would have gotten in school with like just, natural language expressions of, little puzzle problems that you'd have to actually solve some implicit mathematical challenge. For example, like, Janie got 2 apples from her mother and twice as many bananas from her uncle. How many fruit did she get? And here was the discovery that really shocked me, was that at that point in time, if you just took the language models and you would give it a bunch of examples, like here's a word problem, here's an answer, another one and an answer. You give 8 or 10 examples, and then you prompt it with a question. The models were poor. Their accuracy rate was somewhere around the range of like low teens, 11%, 12% accuracy, something really poor. And yet the very same models, if you just augmented the examples a little bit by, instead of just saying, here's a word problem and an answer, you say, here's a word problem, and in natural language, you describe a sequence of reasoning steps that lead to that answer. So for example, Janie got 2 apples from her mother and twice as many bananas from her uncle. How many fruit did she get? You would say, well, she got 2 apples from her mother and twice as many fruit from her uncle. 2 times 2 is 4, so she got 4 fruit from her uncle plus 2, bananas from her mother. That equals 6 fruit. The answer is 6. So you'd literally just write in natural language this explanation chain. So it goes from question to reasoning chain to answer, and add those as examples. The very same model goes from accuracy in low teens up into the high 60s immediately. And the other interesting phenomenon is when you ask the question to the model, it responds with an attempt at a reasoning chain before it generates an answer. So there was this sense in which this started to look, to me at least, like an actual computer, where you were providing a problem and you were eliciting basically an execution sequence, some sort of chain of computational steps on the way to generating answers, which remarkably was also dramatically increasing the accuracy of responding to these answers. And by the way, nowadays, the accuracy on these problems is well into the 90s. Like this is, this isn't just sort of human level performance. This is like actually excellent human level performance on some of these tasks now. Okay, so this, I guess, is some years ago now, and around this point in time, I would get friendly emails from former advisors and other people asking us like, "What's going on here? This is all nonsense, right? These models don't actually reason. Like we've all heard this. They don't actually know anything. They don't actually, have a sort of logic." Fair question, but actually, as I thought about this more, I started to realize like, I think people don't, I think we're not careful enough in how we ask questions like this. So I want to share a little bit of an attempt to reason through what would it mean to answer a question like this. And before I shock you with my answer, I'm going to first actually share a more direct question, which is, instead of asking whether a large language model can reason, why don't we ask something more precise, is can a large language model actually compute? And what I mean by this is, like, is it an actual computer? The nice thing about this is we have definitions of what a computer is. Basically, at least under the Church-Turing thesis, a computer is essentially anything that can be replicated by a Turing machine, right? Any sort of mechanically realizable function is, as far as we understand, right, is something that could be implemented by a Turing machine. And indeed, of course, we know many equivalent notions, right? This idea of universal computation. So within these classes of machines or programming languages, general purpose programming languages, right? We also have this kind of completeness under simulation, or this idea that there exists in these classes a universal programmer machine, a programmer machine that can simulate the execution of any other programmer machine on any input, okay? So you can ask a pretty direct question here, which is a large language model one of these, right, among this class of things? And well, the quick answer is clearly no. Why do I say that? Well, because currently we've gone away from recurrent models of computation, right, and we've moved to transformers, which are actually, have explicitly cut off the recurrence, and they no longer have unbounded memory. Right, so the transformer-based architectures, which are actually the things that are being served right now in these large-scale deployments, actually employ bounded-size context windows. And from a theoretical perspective, there was nothing really interesting about bounded-size computations. Computations on bounded-size inputs, it reduces to like trivial classes like regular expressions or lookup tables. Like, it's just not theoretically interesting. Or put another way, it doesn't really capture what we mean when we say something is a computer. So an LLM on its own cannot be a universal computer unless we go back to recurrence and so on. Maybe state-space models will get us back there. But I just want to share some work that I've been doing recently in trying to understand how close is this really to being a universal model of computation. And the key question to ask is, you take a bounded context window, and the recent models are really huge contexts, like 2 million tokens and so on. Like, that's big, but it's finite. And the question is, what can you do with a model like this to get it to operate on arbitrarily large inputs, like inputs that are vastly larger than whatever context window you happen to be providing at that point in time? And it's quite clear, if you think about this, at some level, all of these models of computation kind of have two key elements. One aspect is there must be some unboundedly large structure, some sort of memory that can grow arbitrarily, but combined with some sort of finitely described decision logic that operates over that structure. Right? That's kind of the hallmark of all of these universal models of computation. So for an LLM, it's kind of like we have to find a way to extend it to operate over some sort of unboundedly large memory, but have the LLM maybe drive this finite decision logic. Okay, so I'm going to share a couple of studies. So the first one you won't like very much, but it'll prove a point. And then the second one's vastly more interesting, but it's work in progress. But anyway, I just want to share this with you, and then we can move on. First study. So a few years ago, I just sat down and thought, like, okay, what would it actually take to do this? So the first study was sort of thinking about augmenting a language model with an external RAM, like some external random access memory where the memory is unboundedly large, and then just trying to ask the question, like, can we really simulate or deploy a universal model of computation this way? And the answer, the punchline's right there. The answer is indeed yes. So I apologize for this long acronym. So at that point in time, what I was trying to set out to prove is that you take a given model. It's not an existence proof. It's not saying within the architecture specified there exists some parameters that could maybe work. No, it's like literally take a model, you don't change the model, you just query it. Can you query this model in a way that drives a universal, computational device? And the answer is yes. So this particular model, FLAN, UPOM, blah, 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 was just some model that it was publicly released that you could prompt in a certain way to elicit general computation. And the construction's pretty straightforward, so I'll just walk you through it. The idea is, we have a large language model, and I'm going to take some arbitrarily large input, and I'm just going to, put the input in some external memory, right? And then I want to simulate the execution of, say, a Turing machine or some program, the execution of, some computational mechanism on this input. And in particular, for a proof like this, I'm going to take some universal Turing machine and simulate its execution on this input string. So to set this up, just augment the memory a little bit with 2 additional memory locations. One, there's going to be a memory location, which I call op, but it's basically an instruction register. It's just going to be a memory location that stores a string, where that string is basically the next prompt to feed into the language model. There's a memory location, which is an address pointer, which points to some other location in the memory. And the way the compute cycle works is it's going to take the string from op, that'll be the next prompt, and then it's just going to splice in the value at the current indexed memory location into that string, and it just feeds that string into the language model. Anyway, if you're interested, there's a paper you can look at. And then the language model responds with an output string, and the output string is simply parsed as a series of assignments to memory locations. And so there's these 2 little regular expression parsers on the input side and the output side. The output is just parsed with a simple regular expression to assign a new value to the memory location, increment or decrement the memory pointer, and where control branching occurs, assign a new string to the instruction register. And it's basically just a von Neumann architecture, and you can run this thing, forever. To get a proof out of this, you take a particular universal machine. There's this interesting universal Turing machine, U15-2. It's basically on the Pareto frontier of the smallest known universal Turing machines. And you can sort of show that this entire apparatus reduces to checking a finite set, in fact, a fairly small set of 29 input-output pairs. Here's 29 prompts. If the model correctly responds to each of those 29, then it will drive this compute engine forever, and it will exactly simulate the execution of that machine on any input, okay? Now, this really is kind of trivial. It's not kind of a big deal. But at least it's sort of the beginning of proving some point that I think thinking of large language models as somehow not about general computation, I believe is a mistake. I think that these are really another form of computational engine that is essentially a universal computer, general purpose computer, admittedly with some memory augmentation. This wasn't that satisfying, to be honest, and so I just want to share some current work that I'm involved in. Now, it's not complete, okay? It's, I'll say that up front, but it's very close, and I think this is even much more interesting and ultimately much more convincing, which is another way to think about extending a large language model to being a general purpose computer is to go back and thinking about what would it take to operate, do proper computation over an arbitrarily large input string that is vastly larger than the context window of the language model. Well, at some level, we could imagine sliding the context window through the string. We're going to have to eventually look at the whole string. Now, as we slide the context window of a language model through a large input, at each step, the language model takes that as the input. It's going to emit some outputs, a token or some sequence of tokens. And the question is, what do you do with those emitted tokens as you're scanning through some large input? And so here, just another kind of thought experiment is, well, one simple thing you can do is you can just take the emitted output tokens and actually just append them to the end of this long input. So you basically just have this memory stream, and any emitted output of the language model you just append, and you just keep going, right? You just slide one step over, autoregressively generate another token, append, another token, append, and so on, and just do this forever. And eventually, eventually you'll start sliding this window over tokens the model itself generated way in the past. And you can start to imagine it can do things like maybe summarize or capture important structures or do something. Seems a bit mysterious, but that's exactly what a computer does. Like a Turing machine reduces everything to some local trivial decision, but a vastly long sequence of locally trivial decisions to do arbitrary computation over arbitrarily large inputs. So the question is a simple streaming model like this, is this actually in principle even able to support universal computation? And interestingly, the answer is yes. You can implement a general computer this way. And in fact, you can prove with some work that you don't even need a large context window. In fact, you can prove that you only need to look at a pair of symbols. And based on a window of size 2, you can generate 1 or 2 output symbols and append them to the end, and you can simulate any Turing machine on any input this way. And if anyone's interested, I go through the construction. But essentially, all it does is, if you think about it a bit, by appending symbols at the end, you can implement a queue, a circular queue. And so really the way the simulation works is it basically rotates memory around up to some control point and then operates at that control point and then rotates memory around as needed to simulate the execution of a Turing machine on that input. Bit tedious, but anyway, let's press on. So now, in particular, for a window size of 2, you can take a particular universal machine. Again, here U15-2, which is a particular universal Turing machine. It has 15 states and 2 input symbols. And you can show that there is a finite set of rules that exactly simulates the execution of that machine on any input. And actually, right now, the rule set is 5,111 rules. This changes every week. It started out at millions and then eventually compressed it to hundreds of thousands, tens of thousands. Anyway, it's a work in progress. But there's some finite set. So we're actually currently engaged in, but we haven't finished, I'll be upfront about that, in trying to show that a current large language model is Turing complete under this streaming model. In particular, this model that's publicly released, Gemini 1.5 Pro. I'll come back to this model later. It's actually an interesting model because this one is one of these incredibly large context models. So the biggest context window right now that you can see publicly with this model is 2 million tokens. Like, it is extremely large. But as it turns out, 5,000 rules doesn't sound like that much, but as you encode it as a string, the smallest encoding we have is already about 40,000 tokens, which already is beyond the capacity of almost all publicly available language models. So even this apparently small rule set is a bit too big for any but the very, very large models currently. So anyway, we're working on it. Maybe just to share the strategy. So the way it works is we're basically just taking the entire rule set and we're going to feed it into the model as the context, and then we'll append it with like the current pair of symbols that it should read from the input. The model will respond with some output. We'll append those to the end. And then we'll shift the pair one step over on the input, keep the same large system prompt, but then slide this small window through the input string. And it'll boil down to the case that if this model makes the exact correct response to each of the 5,111 rules, this would be the end of the proof. It would exactly implement a universal Turing machine. Sadly, it isn't quite there. Okay, so right now we have 14 errors. So it's not proved universal. There is a small augmentation if we shard the rule set into smaller chunks, basically 8 chunks. So that would be like an external machine that detects the range of the symbol pair and then chooses which system prompt to provide. That's perfect. That's a universal computer. Anyway, so that's where we are. Forgive me, I think for the rest of the talk, I'm going to kind of use this as a hypothesis that essentially these models are general purpose compute engines. Technically not fully proved, but it's, there's sort of variations that are proved, and I think it's inevitable. We've made a lot of progress pretty quickly here. I think it's inevitable that we will show this particular model as a universal engine. And a reminder, this is not an existence proof. It's literally the actual live prompting of this frozen model. So it's an actual computer, not a hypothetical computer. Okay. All right, so I want to start transitioning away from this kind of underlying theory of computation to kind of more application focus, but maybe just to wrap up a few points I want to make is at least, okay, in my way of thinking, an LLM, it's not interesting because of natural language. It's interesting because it is a new type of computer, I think. And it's a new type of computer that actually, if necessary, can simulate a classical formal machine, but allows us new modes of interaction that were not available to us previously. So I think this is tremendously exciting. I think there's a lot of opportunity, but of course a lot of challenges and difficulty in working with models of this sort. Another point I need to make is that I'm not trying to make too big a deal out of universality. The fact is, computational universality is a pretty low bar. If you look at some of these proved universal compute mechanisms, they're actually really trivial. It's almost essentially any finite decision logic over some unbounded memory. You know, there's so many of these that are universal. It's kind of like a generic property, not a special property of computation, you know, as long as you have these two elements. One of the big differences, though, if you go between you know, different models of computation, is that for a human to actually you know, elicit the kind of computational behavior you want, like basically programming in these different models, you know, it's dramatically different. It's vastly easier to program in Python than to program in a low-level Turing machine, which is a lot easier than programming in one of these one-dimensional cellular automata. So as a human, these different, you know, formalizations have dramatically different consequences from the perspective of getting the machine to do what you want, okay? But in terms of their ability to simulate each other and simulate arbitrary things, you know, like it's kind of a generic property. It's not that big a deal. Okay, so back to the question. So, you know, can LLMs reason? And so now when people ask me this, I give them very confusing answers because, like, I don't understand the question in some sense. Asking if an LLM can reason is kind of like asking, can a computer reason? And it's kind of like, well, yes and no, right? In some sense, well, yes, to the extent that reasoning is algorithmic, the answer has got to be yes, because if it's algorithmic, we can definitely implement it. But that's kind of a vacuous response, right? Because when people ask the question, can a model reason, they're not really asking, like, is it able in principle to support some kind of algorithmic behavior? They're asking, I think, something more about the interaction. If I address the model in some reasonable way to a human being, is it going to respond in a way that makes sense to me as a human being? I think that's what they're asking. And that's a very different question than a precise mathematical question about the nature of computation. And so I think a lot of our confusion around how do we address these new types of computers and relate it to classical computing science and so on comes down to confusion about what's, you know, fundamental versus what's about human-computer interaction. And I think a lot of it's really about human-computer interaction. Now, some people will violently disagree with me at this point. We can talk offline. Okay, last thing to say before I move on is the more I've been looking at this, the more I've started to be extremely skeptical about the following intuition, which I think many people have, is that somehow by looking at this vast corpus of human-generated strings and simply training to do next token prediction, that our human-generated strings are somehow teaching these models how to become computers, teaching these models how to reason or compute. And the more I've thought about this, the more I've started to think that that is not the case. Now, so I'm going to state a hypothesis that is actually falsifiable. So I think it's a good hypothesis to state, but it's a bit extreme. So I've started to actually believe the following, which is these models, from initialization, were already universal machines. That is, computational universality is a generic property. It's not a special property. It wasn't something that emerged by looking at all this human behavior. It was there right at the start. And we just happened not to wreck it while we were training. And the purpose of all of this next token prediction is simply to make the input-output behavior of this model understandable to us. Now, this could actually be false, right? This hypothesis could be false. Either that randomly initialized transformer is or is not, you know, able to support, you know, universal computation. We're trying to prove something about this. It turns out it's very hard to prove anything about this for the simple reason that essentially we're creating a probability space over a range of computational mechanisms. You know, you can think of it as a distribution over computer-like things, okay? And what we're interested in is an event, a subset. And there's the subset of such machines that happen to support universal computation. The challenge about this is we're trying to compute bounds on the probability of an event where the predicate for that event is an undecidable property. It turns out this is really hard to do. And so I have no idea if we're you know, we've got a couple of toy preliminary things, but I have no idea if we're ever going to get, you know, to a clear answer on this. But it's a mathematically precise statement. It's a bold hypothesis, could well be false. But I find this quite interesting. I actually think this is probably the case, but anyway. Okay, so let me start to make progress here. Okay, so that was just meant to be background, okay? So from here on out, I'm going to act as if these large language models and so on are general purpose computers, and there's going to be all kinds of caveats around that. I apologize, but I want to progress to sort of this mindset that it's this kind of new type of computer that we can work with and use it now to solve problems. And I think after trying to kind of explain things to people who disagree with me, I want to, sorry, forgive me, one more kind of maybe philosophical level discussion. I've started to realize that as computer scientists, you know, me, you, all of us, we were trained in a particular way of thinking about how do you use a computer, like a device, to solve problems for you, a human. And so here's how I express it, is that you, the human, you have a problem you want to solve, like some question you want answered or some, you know, configuration you want to produce. You have a problem. Okay, you bring that problem to this formal machine. This formal machine on its own is not going to do anything. It is not enough for you to bring a problem to that machine. You have to bring a problem to that machine plus two more important things, right? You have to bring a problem plus an exact step-by-step sequence of computational steps that formal machine must execute in order to provide the answer to that problem. But it's actually even harder than that, because if you think about how we're trained to you know, get problems solved with these machines, is that we never really think about, you know, writing a program for a single instance. What you do as a programmer or, you know, a human is that you provide exact step-by-step instructions for solving a problem for every instance of that problem, an entire infinite class of variations of that problem. And you boil it all down to one single recipe, a finitely described algorithm or program, a very precise sequence of steps that will solve all of them. That's your program, and now you go to the formal machine and you say, here's the program, and now here's my problem. You know, run the program, give me the answer, okay? And you know, that's been our field since inception, and we're trained to do this. And you know, it's done a lot of great things. You can do this, but it is very demanding on the human end user. Now, I don't want to be too hyperbolic, but you can imagine now, what does it mean if that formal machine actually can do something like interpret or make sensible guesses about your intent, right? A Python interpreter has no capacity to anticipate your intent in any way whatsoever. A C++ compiler does not anticipate what you meant. The only thing it takes responsibility for is exactly executing exactly what you told it to do and nothing more than that, right? An LLM, which I'm arguing is a general purpose computer, now gives us something a bit more, which is you come to it with your problem, your question, or whatever, and it does attempt, often wrongly, but it does attempt to interpret what you meant to say, what you're trying to do. And this is a profoundly different way of orienting ourselves toward a computational engine, okay? And I think that this, of course, is vastly democratizing and you know, potentially you know, impactful. Of course, we're seeing some of the consequences already. And it's quite interesting that even more than that, an end user in principle can bring a question where they don't have to formalize the question. They just express what they think the question is. The model makes some attempt to interpret what apparently they meant. The end user doesn't need necessarily to know exactly what computational steps to take to solve that problem or answer that question, not even for a single instance. And yet the model will make some lame attempt to respond, okay? So this is a profoundly different form, not of a computer necessarily, but it supports a profoundly different form of human-computer problem-solving activity. And I think that is the big opportunity. Okay, so let me move on. So the interesting thing here is that LLM in principle can sort of allow us now to span the range between, you know, purely informal to purely formal. And I think the real questions of our age, you know, land around how do we navigate this space, you know, to develop real products, real services, you know, solve real problems. and increase the scope, basically, of computing science. And I think we're witnessing that now, but, we're all just trying to make sense out of it. Okay, so let me try to say something about planning. For planning problems, which I guess in my mind are essentially non-deterministic, specifications of non-deterministic computation. That is, you specify a planning problem, it implies or defines some tree of possible execution sequences or tree of possible action sequences within which we're trying to find some serialization or some particular determinization of the computation to find some, successful path or, optimal path. And the question is, how can we leverage, language models, for example, to help us in this endeavor in formulating and solving planning problems? And I can roughly identify three sort of classes of things where we could imagine an LLM helping us. One is, as I've already talked at length about, is this idea that the LLM has some ability to try to interpret informal expressions of intent. It's not going to be precise. It's going to make mistakes. You will misunderstand my intent sometimes, and vice versa. But generally speaking, you are an active listener. You reconstruct the meaning of what I'm saying. And so that's potentially useful, that we can now sort of have informal rather than formal specifications of tasks, but still operate on those tasks in some reasonable way. That seems to be an interesting opportunity here. The second one, I think, is also interesting, and this is where I think the biggest open problems lie, probably, is this idea that in principle these models are trained on a vast, corpus of data. Like, in the sense that these models, I would argue, have seen every written algorithm. Maybe that's hyperbolic, but you could imagine they've essentially seen every algorithm, every data structure, every heuristic. All of it's in there. If it was recorded and posted on the internet, it's in the model. If you query the model, do you know about dynamic programming? The model knows about dynamic programming. It knows about all of these things, okay? So there's an opportunity here as an end user trying to solve problems, but you're not trained, in planning algorithms or computer science in general, the hope might be to leverage this pre-trained knowledge in the model to allow the model to understand intent and to figure out, how you would compute solutions to the problems being brought. This is, as far as I can tell, not really the case yet. I don't see a lot of strong evidence that the models are able yet to do this. I'll come back to this later. I think this is the source of some really profoundly interesting and I think impactful open problems in this space. Okay, the last area of opportunity that I can see here is these models, now have vastly large contexts. And so there is an opportunity to kind of leverage the ability of the models to kind of extrapolate patterns from a large context to produce different, more effective, potentially, output sequences. And so we can imagine for planning problems, like providing many examples of solved problems and hoping somehow that this improves problem-solving performance. So I kind of see at a high level these kind of three categories of things that can help in planning problems and other problem-solving endeavors. Okay, well, I'm running late, so I'm going to have to speed up a bit here. So first, let me just share a couple of studies that we've conducted on these various dimensions. The first one is, indeed, we took some of these very large context models, from the usual suspects, and tried to look at both classical and non-classical planning problems and just try to investigate, is it really the case that if I give you a bunch of demonstrations, that is, here's a specification in PDDL of a planning problem, and then here's an optimal path or a successful plan, and I give you a bunch of examples, and I give you more examples, and now I give you some particular instance of a problem I want to solve. Are we going to see improvements in the ability of an LLM unaided to solve such problems? So that was this first study. And I'll just go through this quickly. So there's three lines here. These are just three different models. The yellow line at the top is this kind of current large Gemini model from Google that has a really large context. And it's kind of interesting, but it's mixed, okay? So one thing we can see is, so these are classical planning domains, blocks, world, logistics, mini-grid. We kind of saw some hope, right, at least on the yellow line. You can see kind of, as you provide more and more examples, it seems to elicit more effective problem-solving behaviors out of the model. There's a clear sense, though, that there's some diminishing returns. At some point, it's not helping so much anymore. And indeed, we see degradation on Block's World. Block's World, I don't know why it's so hard. So it's a bit mixed. But when we look under the hood, I have to confess, Rao was right. When you look at, can these do out of distribution, even with many examples, we don't see out of distribution transfer. So there is kind of a form of just simple retrieval going on here. So like in Block's World, 3 to 7 blocks instances, we can get better at 3 to 7 block instances, but when you go to 15 blocks, it's garbage. So in a sense, despite what I've been saying, the models seem not yet able to kind of capture an implicit algorithm. Like they have some input-output behavior, but they're not really somehow systematically latching on to an underlying generalized core algorithm, it seems. So there is a gap here. Now, the frustrating thing about this is that the model knows about the algorithms. It knows about heuristics. It knows A star, IDA star, like all bidirectional search. It knows it. But it doesn't connect that knowledge, the what part, to the how. So I look at this as a big gap right now in these models, is that they can know about algorithms and they can execute things, but those two things right now are still basically disconnected behaviors. And I think it's an open question on how to get those better connected and to try to actually start to uncover underlying algorithmic structure that should allow out-of-distribution generalization, and we're just not seeing it yet. Okay, here's another study, similar group along the same lines, but it's pushing on this different aspect, which is because the LLMs can process natural language text, right, you can now think about solving planning problems without a formal specification, without like a formal language like PDDL, for example. And so there's these, I think you probably are well aware of these, more aware than me. There are these, natural language planning benchmarks of various kinds of, to me, not very interesting problems like trip planning and so on. But it's, problems that are just written in natural language, like you want to plan a trip through Europe and you have certain constraints. You want to do this, you want to do that, but you can't do this. You want so many of those, right? You just write it in natural language. It's a constraint satisfaction problem. You just want to solve this problem, right? This is a natural expression of real problems that people have. There's a whole range of problems like this, calendar scheduling and so on. And so we since we had everything up and running, we also, could do studies over problems of this type and ran very similar scaling studies, which is, okay, if you're doing, trip planning problems or calendar scheduling problems, can you benefit from just giving a bunch of examples of natural language expressed, planning problems with an actual optimal, plan or a feasible plan provided as examples, and does that improve planning behavior? And it's like, sorta. Very similar diminishing returns. We also see a very similar effect of we're not getting out of distribution generalization. It's essentially the same as if we were in a formal planning context. Now, I think this is exciting, which means we don't really need to be in a formally specified problem regime, and we can still get coherent, problem-solving behavior out of these things. That's interesting. By the way, the y-axis here, you can see these accuracies are poor, like 40%. You can't use this, okay? And this is some of the best models in the world right now. So, there is still a ways to go before this actually becomes something. But I think the meta point I'm trying to make is that we can start to think about expanding the scope of problems that we take on to problems that have informal specification. Okay, I have to skip this part. I'm very late. But I think, of course, formal methods exist. Formal computers, formal algorithms, they exist. You do not need a language model to do arithmetic on natural numbers. That's ridiculous, right? You just call a calculator. And actually, you don't really want a large language model to do anything for which you already have a formalized solution. formal methods are reliable, they're precise, and actually vastly more efficient, right? This is, and so, of course, the real evolution is about how do we acknowledge and get the coexistence of these models of computation, sort of, collaborating in allowing us to effectively solve actual problems. And there's some really fascinating studies on generating code, like competition-level programming, theorem proving, International Math Olympiad, and we're starting to see actual discoveries in computer science of new algorithms and actual discoveries in mathematics around new theorems. Very early days, but these are all formal, informal collaborations. They're not like, just LLMs all the way, nor are they just theorem provers all the way. They're leveraging some strengths and advantages of either. Okay, very quickly, a big change of pace, which is there are other modalities beyond text, right? Obviously speech, images, video. And so I just want to briefly share some work we've been doing on planning problems or sequential decision making by leveraging video generation, believe it or not, as a medium for solving these problems. And up front, I was pretty skeptical, but it's been quite interesting. So there's a series of works now in this space. And so here's how I kind of express it, which is another way to express informal intent is like we can use natural language to express things like goals or things we want to do, but sometimes the things we want to do are like actual, physical manipulation in the real world, like actual navigation or manipulation. And in those contexts, you can do something by using like an image, take a picture of a scenario, have a natural language expression of what you want to do, and then leverage basically video as a sequential decision-making process or a rendering of a sequence of computational steps from an initial image to some sort of goal. And we actually kind of got something interesting going here. So the idea is you can learn a text condition video generation model, some big diffusion model that conditions on various things. And we're sort of thinking of some robotics, simple manipulation deployments. But there's a lot of kind of natural, like kitchen, manipulations and so on. So you ingest a bunch of videos, and here we use basically publicly available videos, ingest a bunch of videos into a video diffusion model, and train a model that can kind of condition on a natural language express goal and an initial image of a situation. And then have the video generator basically generate a video, which is a sequence of steps to achieve a goal outcome. Let me just sort of give you an example. So here's some synthetic robot manipulation problem where that first image is like just a picture. So here's a configuration. We have a goal, put an orange block left of a red block, and then the rest is a generated video, which shows this kind of simulated robot arm picking things up and moving them around and achieving the goal. What was really interesting about this, though, is that like we have this mix of synthetic and real images in the model, is that we can take the same model, and now we can take a real image of a real cluttered lab environment with all kinds of stuff in the way, but a robot manipulator with stuff, and give it a goal, and it generates a video showing, manipulations, basically a video, which is all synthetic. Of the manipulator doing things with these real objects. Now, in terms of planning, what you want to get is the action sequence. So we will also learn an inverse dynamics model. So a subset of the data will be like synthetic data we produce where we know the action sequence, and we will learn an inverse dynamics model and kind of fuse that with the video generation. So we can extract the action sequence from the generated video. And so we've kind of, that was maybe 2 years ago, we've kind of pushed forward on this, and we've now got ourselves to a position where we can fuse a much larger set of data and videos of different types, like sort of egocentric motion, for navigation, moving in real world environments, and a lot more robot manipulation data and so on. Of course, in terms of action recovery, we need to use robot manipulation data where we know ground truth action sequences to get an inverse dynamics model. So here's another demonstration. So what's interesting is that these are all synthetic videos. These are not videos of any real thing, but you can see, there's a tabletop and a cloth, and that's the first image. And then, we have this, just simple commands like uncover, different objects. And you can see that the video generation model understands things about the world. What I mean is the cloth, when it gets picked up, looks like a cloth. It's, it's flexible and so on. The tabletop acts like a tabletop. The objects look like objects. By the way, that hand doesn't exist. That hand is hallucinated from all the data. Just imagine some human-like hand going in and picking up a cloth and revealing stuff. Here's another demonstration in a kitchen of various manipulations in a kitchen, and all of these are hallucinated videos that actually they're not perfect, but they actually look realistic. And I think you've seen that video generation is now getting to a point that's pretty interesting. And so there are a bunch of robotics-like scenarios that we had in mind where this is all hallucinated video, like somebody's leg is in the first frame, so it just imagines what's going on. And you can sort of chain together sequences of natural language sub-goals and kind of get a long, sequence of video from which we can try to extract by inverse dynamics, the actual control operations for the arm. And so we have actually attempted some sim-to-real transfer. So the video on the left is actually a real robot in a real environment, and all the stuff on the right are hallucinated videos showing some initial frame and some configuration and some imagined sequence of actions. And we were actually able to see zero-shot transfer to the real robot. So we would use these video planners to come up with an action sequence, imagine through video, use the inverse dynamics model, and then just actually run it out of the box on the real robot arm. And it actually did better than previous sim-to-real transfer techniques that were being tried. Now, I don't want to push this too hard. It's still, these are simplistic demos. It's not that elaborate yet. But I think the big point here is that a lot of the current focus around video generation is for entertainment and fun, and that's fine. But actually, I think there's a lot of real utility in video as a medium for actually thinking about real-world decision-making and real-world planning problems. And this seems to be a big opportunity that is just kind of open, as far as I can tell. And I really need to wrap up. Maybe one thing to say is we're not doing this yet, but you can imagine, right, when you have real-world planning problems, like, there's something in your HVAC, you have to replace the filter, or you have to replace something in your car. What do? You go to YouTube, you search around for something that looks similar and somebody's solving the problem you're trying to solve. We're actually starting to see the possibility that you literally just take a picture and then synthesize a video that shows you the how-to and so on. Now, it's not there yet, but that's the kind of thing that you can start to imagine now. Okay, so I need to wrap up. I do apologize for running over, and I also apologize that I'm not trying to sell. I think it's just that I'm trying to share a perspective that there are big opportunities. There are big challenges. It is not a battle of informal versus formal computing. I think it's just an opportunity space that has opened up that nobody really understands right now. But clearly, we have the opportunity now to really inform the future by, trying to identify coherent, useful, reasonable steps towards, exploiting and leveraging these new capabilities in these models. And with that, I should thank my many great collaborators, and thanks for your attention.